Hey everybody, Gabe Jenkins back with you to talk about properties of metals. We are in the kind of the second part of this class. We just learned about the atomic structure of materials, atoms, molecules, ionic bonds, covalent bonds, most importantly, metallic bonds, and we learned how all the little atoms inside a metal are joined by metallic bonds, and that informs a lot of why they act the way they act in terms of like their ductility, or which is the ability to be pulled into a long string without just breaking. Their malleability, the ability of a material to be able to like be hit or pounded and take shape and not just shatter. Also determines things like their electrical and thermal conductivity and their shininess, things like that. So we just learned all about that in our last PowerPoint. Today we're going to do starting just two quick PowerPoints where we talk about metals in a little bit more depth, because when we get into manufacturing, it is the properties of metals that we are, at least in this class, going to be the most interested in, because we're going to spend a lot of time going forward looking at things like milling and turning, and specifically using CNC mills and lathes in order to manufacture work. So we are going to dive a little bit here into properties of metals. And so we learned like what's the underlying structure of them. Today we're going to learn about what are some of the properties that we care about and how do we measure those properties of metals, okay? We're going to learn about something called the stress-strain curve, so the relationship between how much pressure or force you apply to an object and how it changes its shape as a result of those things. Stress is the force, in a way, and strain is how much it stretches or compresses or moves. We're going to do a pretty deep dive into the tensile test, which is a test where you take a piece of material and you pull on it and you see how much force you have to apply to it in terms of pulling on it in order to make it stretch out, which is related to ductility. And then kind of the reverse of that is compression, which is if you squish something together, how much force do you have to apply to it till it squishes and stays permanently squished. So that's what this PowerPoint's going to be about. We're going to need to understand a graph in a lot of detail when it comes to stress-strain relationships, and we're going to need to be able to interpret that graph and explain how the math works and how the graph itself depicts what's going on in a sample of metal when it's undergoing either a tensile test or a compression test. So let's dive in. We are in this part. We are only worried about mechanical properties of different materials. We are not, and mechanical meaning like physical, like you're pushing on it, pulling on it. Those are mechanical forces, and so we are most interested in this PowerPoint on what are the properties of a material, whether it's a metal, like an elemental metal or an alloy or anything. What are the properties of a material when we subject it to mechanical stresses, when we pull on it, when we compress it? What are the properties of that specific type of material? How does it respond? So we're going to look at things like elastic modulus, which is going to be a measure of how elastic a material is when you subject it to force. Ductility, which is related, that's the ability of a material to be stretched and pulled. In future ones, we're going to look at hardness, and we're going to look at other measures of strength, but that's not today. Here is kind of an underlying truth of the world, and a harsh truth about manufacturing, is that very often the mechanical properties that are desirable to a designer of a material, such as high strength, are really problematic when it comes to manufacturing. Like you want something to get into a specific shape, and you want it to maintain that shape and not get dented and not get pulled out of shape, not get ripped, not get torn. You want it to be a strong material. Well, the very fact that you want it to be strong is what makes it hard to manufacture, because if it's hard to change to get into the shape you want, whether it's by cutting it or pounding it, that's also going to make it hard to get into that shape in the first place, right? So it's just kind of it's a foundational truth of manufacturing for the most part when you're dealing with metals, is that the things that make it so, the properties of a material that make it good as a product very often are what make it very difficult to manufacture. And so I hope that as part of your ongoing understanding of how manufacturing and design are related, I hope that you over time develop an understanding that as a designer, it's really critically important to think about how that thing that you're designing is going to be manufactured. Can it be manufactured or can it not, right? And as a manufacturing engineer, you should also be aware of what is the design intent of the designer, okay? So let's go. We are going to be talking about something called the strain stress or stress strain relationship, okay? So we're going to be looking at really just two forces today, tensile force and compressive force. Those are different stresses. It says there are three types of static stresses to which materials can be subjected. Static simply means that the two objects, or that there is a force applied to an object and nothing is in motion, right? If I take this piece of metal and pull on it, I'm pulling on each side, pulling it apart, nothing's moving, right? Similarly, if I take this piece of metal and I push on the top and push on the bottom, nothing's moving. It is I'm exerting a static stress onto that material because nothing's moving. Shear, so tensile is when you pull on something. Compressive force is when you push two sides of an object together. And shear is when you take a piece of material, you pull one direction, like one side of the object gets pulled in one direction, and the other side gets pulled in the other direction. So you're kind of like causing two sides of the object to like kind of you're pushing one like this and the other like that. That's a shear stress. All right. And so manufacturing scientists and manufacturers have developed a way of analyzing materials to subject materials to these different stresses and then measure what happens. When they measure what happens, they are trying to understand how the material responds and how to depict that response in a graph. So the various tests that we're going to talk about today, like if you take a material, right, you can pull on the top and pull on the bottom. That is a tensile strength test. Pulling on the top, pulling on the bottom, seeing how much it stretches apart when you pull on it. A flexure test kind of like pulls up on the sides and pushes down in the middle. Sometimes it's a 3-point test like this. Sometimes it's a 4-point test. But either way, you're kind of like seeing how much force it requires to bend a material. This is a compression test right here where you push down on the top, push up on the bottom, and you're trying to see how much force required to make it squish permanently. And then this is an example of the shear stress test where you're pushing down on one side, up on the other, and you're basically trying to see how much force has to be applied in different directions in order to cause that material to either bend, or if there's a bond between these two parts, how much is required to break that bond. Okay? These are the different kinds of tests we're talking about today. Okay. So we're going to dive in deeply into the tensile strength test. It's the most common test for studying the strain stress or stress strain relationship in a material. It's the easiest to conduct, and pretty much every materials lab you ever visit that has anything to do with manufacturing is going to have a little setup where they have a machine that will pull on a piece of material and see how much force is required to make it bend. Okay, so what you see here is kind of just a simplified view of what happens. You can imagine a certain material, imagine a rod of metal, right? Something that's just like a straight up like little cylinder of metal, and it's got a certain height or a length, we'll call it. And it's got a certain area, like a cross section. If you were to take this cylinder and cut it along a line like from here to here, and look at it, you would see a cylinder, you'd see a circle, right? What the tensile strength test does is it pulls upwards with a force F, and it pulls downward with a force F. And when it pulls on that cylinder of material, the cylinder, it lengthens, it gets longer, right? Also, because it's getting longer, the surface area, the cross section, like if you were to cut this piece, this circle here is slightly smaller surface area than this surface, right? It's because it's stretching out, right? So you can understand that when this whole cylinder stretches out, the cross section, the area gets smaller, okay? And what you're doing in a stress test is you're measuring how much force you're applying, and then you're seeing how much does it lengthen before it kind of changes permanently, okay? So The specimen itself looks like this. It's got little threads at the top, little threads at the bottom, and that allows you to kind of like screw it into a machine so that when you pull on it, it's held in place. And what you're really measuring is what happens to the length of the material from here to here. Okay, there's little lines at the top and lines at the bottom, and what you're really doing is you're measuring how far those things stretch apart before the material starts to bend and break. All right, so there's a machine. It looks like this. There's a top crosshead. There's a bottom crosshead, and the material itself is the test specimen is locked right here in the middle. This pulls up, this pulls down, and eventually you pull until it breaks, and then the test is over. All right. So here's what happens in a tensile test. When you do a tensile test, here's what happens. Right at the very beginning of the test, with no force on it, no load is what it's called. There's no mechanical stress load on it. It is height L. We say L naught. This little zero down below the L means like this is the originating. This is the zero length. This is like the length of the rod before you start the test. Okay. After you start pulling, after you exert a force on the top and on the bottom, pulling it up and down like this, in the very beginning of the test, the material starts to stretch, and it stresses in a uniform way, meaning that there's no part of this that is getting stretched any more than any other part, right? And so it is uniform elongation is what it's called. Elongation just means getting longer. So it is uniformly elongating, and uniformly the cross-sectional area is getting smaller, right? It's getting skinnier as a tube, right? And the more and more pressure you put on it, it will continue to elongate and continue to get a thinner cross section until it can't just stretch anymore. At that point, there's a critical moment when you've exerted enough force per surface area where the material gives. It can't just stretch anymore, and it starts to get skinnier at one particular point. We call this point the neck. Okay, it's like the neck. Imagine that it's like a head, that's a body. The neck is right in the middle. The neck is skinnier than the rest of it. And at that point in the test, all of the additional force that gets pulled up and pulled down on the object, all of that additional force gets concentrated on the neck, and the neck itself stretches out until it fractures and breaks. At that point, the test is over, and scientists start to look at, okay, how much force was required to cause it to neck? How much was required to make it break entirely? And then they measure those things and graph it. Okay? So if you look at it like this, this is what it looks like. It starts off kind of like normal before any load. It stretches uniformly. You can see maybe here at the beginning, there's just a tiniest little hint of a neck. This is what a neck looks like because the material is getting skinnier at that one part. At that moment, all of the force that you're pulling up and pulling down, all of that force gets concentrated right there, and then eventually it just breaks. Okay. It's important to note that before it starts to neck, so any point over here when it's just uniformly elongating, if you release the pressure, if you stop pulling on it, the material should bounce back to its original length and original cross section, right? It should. Okay, so the idea here is that you can pull on any material for a certain length, a certain amount of force per surface area, and it'll stretch a tiny bit, but if you let go, it'll bounce back to its original shape. But if you pull on it with enough force per surface area, it can't bounce back. It's going to be permanently stretched, and it's never going to bounce back to its original length and its original surface area. Okay, so here is what you. It's kind of just like a sideways view of what we just saw before we do the test at all. We measure the length, which is L naught. As we do the test, we continue to measure the length, which is the length, and here it's LE, which is length of elongation, Don't worry about the L, the E, and the U. But it's going to continue to stretch until it starts to, it reaches a point where it cannot bounce back to its original length. At that point, it starts to neck, and then it continues. All the force gets concentrated right here until it breaks. That relationship between how much stress, how much force per surface area you're putting on the object, which is called stress, we'll come back to that in a second. There's a relationship between how much force you put on something and how much it can stretch before it cannot bounce back to its original length. So let's look at it. This stress strain curve is going to be important for your quiz, and it's important that you be able to explain what it means. What this is saying is that this is a graph that has it's a two-axis graph, right? So on the x-axis here is measuring strain. Strain measures basically how much the length of the object changes as a percentage of its original length. So in order to calculate strain, which is represented by the variable lowercase e, to calculate that, you take whatever length the material is at any point during the test, you subtract out the original length, and then you divide that difference by the original length. So, for example, say the original length of the rod was 10 millimeters, L naught, and say you pulling on it and it stretches until it is a length of 12 instead of 10. It's gotten 2 millimeters longer, right? And so if you were trying to measure strain at that point, we would take 12, which is the current length, minus 10, and then divide it by 10. So it would be 12 minus 10 is 2, divided by 10, so it's 0.2 is the answer. So strain would be 0.2 in that case. Okay? So it's basically saying, as a percentage, how much has the length changed. On the y-axis, we have stress. Okay? And stress is represented as force, which is here, P, divided by surface area. So it's like if you're doing the stress test on a really fat piece of material, you're going to obviously have to pull more on it to make that big fat piece of material with a big surface area. You have to pull more to make it move at all, to make it stretch, right? And so if you're pulling on a very skinny thing like a paper clip, requires less force in order to make it stretch apart. All right? So what this is measuring is the y-axis is measuring how much stress you're placing on the object, and the x-axis is how much the length of the object is changing over time. What this graph shows you is that as you're pulling on an object during the tensile stress test, for the first amount of force that you're pulling on it, it's stretching out. So as you can see, as I exert more and more force, which is shown on the y-axis, you can see that the x-axis is getting a little bit longer, a little bit longer, a little bit longer. And if at any point during this stress test, if say I only pull up to this amount of stress right here, if I do, and then I let go, the material itself will bounce right back to its original length. Okay? It will just absolutely come back to its original length. But there is a point where if I continue to increase, you'll also notice that the line here is linear. It is not curved at all. It's a straight line. That means that the amount of stress you pull on an object, it is uniformly getting longer. It's not like doing anything that it's getting more and more longer, more and more length and elongated. It's just if I pull 20% more, it's going to stretch 20% more, whatever it is. But if I let go, it's going to bounce back to its original length. But there's a certain amount of force for any type of material. There's a characteristic amount of stress that you can put on that material, where if you put more pounds per square inch or newtons per square millimeter, however you want to measure this, if you put enough stress on it, that material will then start to lengthen even faster. Okay, it's going to stretch faster and faster and faster. And once it gets curved here, it is not going to ever bounce back to its original length. You can imagine pulling on a paper clip And if you've ever played with a paper clip, you can kind of bend it a little bit either way, and it's going to bounce back to its original shape. But if you bend it enough, it's just going to remain permanently bent. That's the idea of yield stress. Okay, and so as soon as this graph turns curved, at this point right here, it's never going to bounce back to its original length. Okay, that's called the yield stress. It's the amount of stress that you have to place on it so that it permanently changes. That object is going to continue to get longer and longer and longer, and you can see that as it requires less and less and less force to make it bend the same amount. It's getting easier and easier to bend. At some point, it's going to start necking, like we showed in the picture. And once it starts to reach that necking point, all of the force that gets exerted on that object is causing it to lengthen it and lengthen and lengthen, which is why this graph starts to go down, meaning it requires less and less and less force. Once it started necking, it's requiring less and less and less force to make it stretch more and more and more. Eventually, though, the material itself is going to break, it's going to fracture, and at that point, it's broken, right? The first part of this graph, from here all the way over to the yield stress point, we say that this part of the stress-strain relationship is elastic. Elastic simply means that it will bounce back. Think of it like elastic in a waistband. It'll bounce back. From the yield stress point on, anything over here where it is curved, we say that the stress-strain relationship, the curve, is plastic. And plastic just means it's changed, right? It's never coming back. And so anything on the left will bounce back to its original length, even if you let the force off of it. Once it is past that point, though, the object is permanently changed. That part of the graph is plastic. So here we see just a kind of a version of the same graph, but this is what happens if you apply this tensile force to it for a while. It reaches this first part again is elastic, and so it'll bounce back. If I took the force off right here, it would just bounce back to its original length. The strain would go back to zero. But right around here somewhere, the graph turns curved, it turns non-linear, and at that point, it is past the yield stress point, and at this point, the graph is plastic. Right? The material itself has changed permanently. Now, it might be that if I let go of the force on it, just like stop pulling on it anymore, what's going to happen is it's going to bounce back a little bit, right? The strain is going to get lower, meaning it's not going to be as stretched as it was at the maximum stretch point, but it's never, ever, ever going to get back to this starting length. And so the difference between the starting length and where it kind of bounced back to is known as its permanent deformation, right? It's like permanently, that's as long as it's going to stay. All right, so here is a video showing the test, and it kind of like shows the test along with the graph, so you can kind of begin to connect parts of the graph with parts of the with parts of the test itself.